Welcome back to the podcast. Today we're diving into a crucial topic that can significantly impact the integrity of your data: race conditions in database transactions. We'll focus on two specific issues: lost updates and write skew. These problems can lead to subtle bugs that are often hard to catch during testing. So it's essential to understand them and explore effective prevention strategies. Let's start with lost updates. This situation arises when two transactions read the same data and then try to update it at the same time, resulting in one of the updates being overwritten or lost. The traditional approach to handle this is through atomic operations provided by the database. However, there are times when these operations fall short, especially when specific application logic needs to be maintained. For example, think about a game where two players are trying to move the same piece on a board. In this scenario, a simple atomic operation won't cut it. You also need to enforce the game rules, which is where explicit locking comes into play. By locking the object being updated, you can ensure that if one player is making a move, the other player has to wait until that action is completed. In our game example, a transaction would lock the game piece for an update. Check if the move is valid, and then commit the change. However, there's a catch. It's easy to overlook adding these locks in your code, which can lead to race conditions. To help with this, some databases allow for concurrent execution of transactions. If a lost update is detected, the transaction manager will abort and force a retry. But not all databases handle this consistently. For instance, while Postgres and Oracle have mechanisms to detect lost updates, MySQL's repeatable read isolation level doesn't, which can create confusion about whether a database truly provides snapshot isolation. Now let's shift gears and discuss atomic compare and set operations. These operations help prevent lost updates by allowing an update only if the value hasn't changed since it was last read. But you need to tread carefully here. If the database allows the where clause to read from an old snapshot, you might still encounter lost updates. So it's crucial to verify your database's implementation of this feature before relying on it. As we move on to replicated databases, the challenge of preventing lost updates becomes even more complex. In these systems, multiple nodes can modify data concurrently, making it tough to maintain a single up-to-date copy. Techniques like locks or compare and set operations often don't apply here. Instead, a common approach is to let conflicting versions of data coexist and resolve these conflicts later. This is where commutative operations come into play, as they can be applied in different orders across replicas without losing updates. For instance, RIAC 2.0 uses this concept to automatically merge updates. Next, let's explore write skew, which is a subtler form of race condition. Picture two doctors at a hospital who both want to take leave at the same time. Each transaction checks that there are still enough doctors on call before proceeding to update their status. If both transactions run concurrently, they might both succeed, leaving the hospital without any doctors available. This anomaly, known as write skew, can be tricky because it doesn't involve dirty writes or lost updates. Rather, it's a conflict that arises from concurrent transactions updating different objects. Preventing write skew is more challenging than preventing lost updates. Atomic single object operations won't help here, since multiple objects are involved. Additionally, the automatic detection of lost updates in some databases doesn't cover write skew. To effectively manage this, you might need to implement serializable isolation, which ensures that transactions are executed in a way that prevents such conflicts. In some cases, database constraints can enforce rules. For example, if you want to ensure that at least one doctor is on call, you could implement a constraint that checks multiple records. However, not all databases support this feature out of the box. So you might need to get creative with triggers or materialized views. If serializable isolation isn't an option, another approach is to explicitly lock the rows that your transactions depend on. In our doctor example, you could write a transaction that locks the doctor records before updating their on-call status. This way, you ensure that no two doctors can go off-call simultaneously. As we wrap up our discussion, it's important to recognize that race conditions like lost updates and right skew are not just theoretical concepts. They can have real-world implications for your applications. Being aware of these issues allows you to design your database interactions more thoughtfully, ensuring data integrity and preventing those subtle bugs from creeping into your system. Today, we've explored the complexities of race conditions in database transactions, focusing on lost updates and right skew. We've discussed various strategies for preventing these issues, from using explicit locks to implementing serializable isolation. As you continue your journey in database management, keep these concepts in mind to safeguard your applications against potential pitfalls. Thanks for tuning in. And we'll catch you next time for more insights into the fascinating world of databases.